Next question. Why should the work done, as we've calculated, be equal to the sum of the change in kinetic and change in potential energies? Well, the obvious answer is the work-energy theorem. The work done by non-conservative forces on any system or object is equal to the change in potential plus the change in kinetic energy. So, the change in kinetic energy of the volume increment in this case, or in any case, is what? Well, first of all, change in kinetic energy is equal to the change in 1/2 mv squared. That's what we mean by kinetic energy. That's the formula for kinetic energy, is this change in kinetic energy. The mass of the delta V increment is just rho times delta V, density times the volume increment. So that the change in kinetic energy is the change in 1/2 mv squared. M can be replaced with rho delta V, and we get this expression. Now what about the change in potential energy? As much as I hate mgh or mgy as a first point, a first assumption, because as I commented in class, people will apply it to orbital mechanics at the distance of the moon. And use the G at the surface of the Earth to do it. This is not your definition of gravitational potential energy. The definition of gravitational potential energy is equal and opposite to the work done by the gravitational force. But for the restricted situation here, we don't have bodies of water that extend from here to the moon. They don't extend far from the surface of the Earth, and in this case, we're pretty safe using this formula. We don't have significant changes in G for any body of water in the vicinity of the surface of the Earth. And if you get that far away from the surface of the Earth, your science had better be good enough to compensate. So for the cases that we have here, we have change in mgy. And M is, again, rho delta V, so that the change in potential energy is just this. Okay? So if we put the work-energy theorem together with what we've got here, I've written the work-energy theorem out again. It's clear that the work being done here, that the work we've been talking about, is the work done on that volume by the pressure. Okay? So the work, that force is non-conservative. The work done by non-conservative forces is the work done by the pressure on the volume increment. And that's negative P delta V. Again, we explained the negative. We're going from higher to lower pressure. In the situation we're talking about. Okay, the change in potential energy, change in kinetic energy, well, we've explained these two expressions. We just use them here. And then we do the obvious thing. We divide by delta V, and we get this, and I don't need to read it to you. And then we simply rearrange this so all the quantities are on the same side, and we'll make them all positive rather than making them all negative. And this is one form of Bernoullis equation. And I think it's in my opinion, it's the preferred form if you want to talk about what's really going on and if you want to understand the equation. Now, if you just want to write down a bunch of symbols and use a formula, this version is okay. But I tend to advocate that you understand it here and understand that delta P is just P2 minus P1. Delta of rho gy is just rho gy2 minus rho gy1. And this is 1/2 mv2 squared minus 1/2 mv1 squared. That's what we mean by the change in each of these quantities. And side comment, we're assuming that rho is constant and G is constant. In other words, we're assuming an incompressible fluid. We're assuming we're close to the surface of the Earth. This also applies to like air, for rho isn't necessarily constant. Density of air can certainly vary in an airflow. Density varies all the time. The atmospheric pressure varies all the time. which varies the density of the air. Okay, but for the case where the only variables are pressure, altitude, and velocity, then we have a pressure 1, a pressure 2, and we very easily get this equation from this equation. Okay, and that's also called Bernoullis equation. Now, just very quickly, if one of these quantities remains the same so that its change is 0, then if one of the other quantities increases, the remaining third quantity has to decrease, because if one of these changes is 0 and one of these others is positive, then the remaining has to be negative. And that's a very important thing to understand. And we'll talk more about the applications of Bernoullis equations, but it's important for you to understand where it comes from, and that helps you understand how it can be applied.